All right, everybody. It is that time for the AP Physics C electricity and magnetism version J FRQs. I believe yes, they are version J. Yeah, it took a little bit longer for College Board to release these than I thought they were, but here we are. So let's just go ahead and dive right into it. There's four questions. And I feel like I'm probably going to be a bit more confident with these ones than I was with the mechanics ones, mainly because I kind of enjoy E&M a lot more than I do mechanics, if you couldn't tell by my modern physics videos that have been coming out. Anyway, so you have two long current carrying wires. They're both parallel, and one of them has a radius of 2a and is centered at x0, and the other is, let's see, at 10a. Okay, so they both have the same total current, and yeah, and then they have their own current densities. Wire T is uniform, and wire S goes like C times R. Okay, so part one, we can go ahead and start that one. So it says derive an expression for the magnetic field at point P due only to the current in wire S. Okay, so that's not too bad. We have to start that by using Ampere's law. Because this is a cylinder, Ampere's law actually works really well. So this is what it looks like. And then we can say, sorry, I'm going to have to go over here, but I enclosed is going to equal integral of J dA then, the current density that is. Um, we can say then that you have B times 2 pi r, which is the length of an Amperian circle, or the circumference. So that works. And then that's going to equal mu naught times the integral from 0 to r of your current density multiplied by 2 pi r dr. Now here we're making use of, I'm going to write because dA is equal to 2 pi r dr. We know that because the area that we're trying to integrate the current density over is a circle. Circle is area of pi r squared. You differentiate that with respect to r, you get 2 pi r dr then. So we've got b times 2 pi r equals mu naught times 2/3 pi c r cubed. I think I did that correctly. Let's see, r squared. Yes, pull down a 3, increase the power by 1 then. So that means that b is going to equal mu naught c r squared, that is, over 3. There we go. Not too bad, actually. But it does, wait, sorry, I shouldn't have boxed that because I just saw too that it says that you must represent in terms of A. Now, we know that R is equal to A itself because that is where point P is located relative to the central axis. So B must be equal to mu naught C A squared over 3. Glad I caught that actually. Otherwise, that would have been a point off for me. So there you go. On the axes below, sketch the magnetic field due to the currents of both wires. Okay. So first things first, I'm going to say that we have the first thing I want to kind of do is I want to figure out how the magnetic fields are going to look if you're between 2 and 9A. So due to wire S, the magnetic field will be into the page, and actually also due to wire T by the right hand rule. So that's kind of nice then. We can make use of that. If we want to find the total magnetic field, it's actually not too bad because we know that you can calculate the total magnetic field at any of these points by taking Ampere's law twice and then just superimposing them. So the total magnetic field should be the magnetic field due to wire S plus the magnetic field due to wire T then. Magnetic field due to wire S is going to be in magnitude mu naught I over 2 pi r. I believe it's I0 for the enclosed current because that's what the total current of the wire is. And then you would have to say plus mu naught I0 over 2 pi. Sorry, I'm going to change this to x, and then this one would be 10 minus x, 10a minus x rather. So that's going to give us the total magnetic field. We know that because the distance between the central axis of wire t, and the point that we want to find the field is 10A minus the actual position then. So the total magnetic field, if we actually simplify that, you're going to get mu naught I over 2x, sorry, 2 pi, and then 10A minus x plus x over, uh, let's see, x times 10A minus x. Now here's the one issue is I don't exactly know how that's going to look. It's going to be some sort of like inverse graph, but then it's a 1 over, it's going to be proportional to 1 over uh, x 10A minus x. So I am going to need to go ahead and plug in my second monitor, and hopefully that won't screw things up on here. Because I don't actually know how that graph looks off the top of my head. I know it's some sort of inverse squared graph. Uh, I know that's some sort of inverse squared graph, but I do want to actually figure out what that looks like as well, too. So I'm going to go ahead and pull up Desmos on my second monitor. You won't be able to see that. Whoops. There we go. You won't be able to see it, but I just need to do it because I want to make sure I have the correct graph for you guys. Now, of course, you are allowed Desmos on the AP exam, so it's not like I'm, cheating or anything, but okay. All right, there we go. Yeah, it was pretty easy actually. It's the actual graph itself should kind of be unbound, of course, at 0 and 10A. And I know that says that that things outside of the sorry, I'm trying to concentrate while I'm drawing this. Things outside of the inside the shaded region will not be graded. So let's see. So we would expect for something like this. It's not going to go up to infinity at 9A yet, because the wire itself is located, the central axis of the wire is located at 10A. So it should look something like this. Not exactly though. Let's see. So two looks like that. I've got Desmos pulled up on this side. Okay. So yeah, it looks something along the lines like this. I believe that the minimum is going to be halfway in between both of these central axes. That makes sense. So it should be at 5A. So there we go. It's just a sketch anyway. So I think this is all they're really looking for here. So I'm going to write that this is a minimum, just because I can. So that'll, hopefully kind of look okay. So, all right. So it's just a sketch anyway, but it should look something along the lines like this. 9A should have a bigger magnetic field than 2A, because you are closer to the central axis of one wire compared to when you were at 2A. So something along the lines like that. It should actually be a symmetric graph though. So you know what? I'm going to go ahead and redraw that. It should be mostly symmetric between 0 and 10A. So it should look, this is not my best work. Um, Something along the lines like this. My goodness, I'm so bad at drawing on this tablet. And then shoot, I didn't mean to do that. Sorry, guys. There we go. Okay, I'm just gonna leave it like that. Of course, you would stop it between 2A and 9A. So you don't have to draw from 0 to 2A, or of course past 9A. But past 9A, it would go unbounded to infinity at the value of 10A. It'd be an asymptote there. So, okay. Part B, the instant shown, you have a charge. That charge experiences a force, and we want to figure out the magnitude of the force. Okay, so via the right-hand rule, we still know that the total magnetic field itself is into the page. And then by the right-hand rule, that means that you have an upward force. So it's pointing towards the top of the page then. That's by the right-hand rule. So I'm going to go ahead and start writing that down. Right, so by the right-hand rule, the force is toward top of the page, which is actually in the y-hat direction because it says we're on the xy plane. So we got to write that down. And then we can say, all right, well, F is equal to Q. Q is not a vector. V cross B. But from the previous parts, we know that the total magnetic field is going to be mu naught I naught over 2 pi x plus mu naught I naught. I don't know why I didn't just write it in the simplified form, but here you go. Something along the lines like that. Here's what the simplified form looks like. It was mu naught I naught times 10a all over 2 pi times x, which x in this case is 5a. So we'll multiply this by 5a, and then 10a minus 5a. So this is the equation that I used to help me with my graph. We can cancel quite a bit of stuff out. You got mu naught I naught over a, not a, sorry, pi. Uh, and then times 5a then left over. So that's the magnetic field. And then to solve for the force, we have F is equal to Q times V times mu naught I naught over 5 pi a then. Yeah, there we go. And we're going to also have QV cross B is equal to QVB sine phi equals QVB here because the magnetic field is into the page and the velocity is to the right, so they're perpendicular. Okay, first question done. Very nice. All right, so let's go ahead and delete this. You have a thin non-conducting charged rod, so they're insulators, -3 to -L, and then L to 3. Okay. All right, point P is located at -2L. Okay, so they both have the same positive charge density. So draw the following two tasks in figure 2. Let's see. Draw an arrow starting on the dot that indicates the direction of the net electric field at point P. That's not too bad. Then the net electric field at the origin, also not too bad. And then draw an arrow to indicate the direction of a negative charge at the origin. Oh, also not bad. Okay. Well, both of the electric fields are going to be away from the two rods, so you would expect because the let's see, draw an arrow that indicates the direction. Okay, so we don't care about magnitude, so all of these are going to look just like this. So they're all going to be at 45-degree angles because point P, the origin, are both equal distance away from both of the rods then. Both of the rods have positive charge density, so their electric field should point away from the two rods. And then because you have a negative charge, the negative charge is going to accelerate in a direction opposite of the electric field. All right, derive an expression for the net electric field at the origin and its magnitude, which means that we're going to have to solve for the components of both of these and then just use Pythagorean theorem. That's actually not as bad as it might sound because you can notice that because of symmetry, the x and the y components of the electric field have the same magnitude. So here is the formula I would like to start with from our equation sheet. And I am going to solve it from rod S because we do know, I'm going to say EX, and this is from rod S. And actually, no, sorry. There we go. Let's write it like that because it's on our equation sheet like that. So we can say that E is equal to EX from rod S, and E is equal to negative EY from rod T. Again, the symmetry of this problem says that they should have equal magnitude, so then the total electric field magnitude should be the square root of EX squared plus EY squared, which is actually going to equal square root of 2EX squared then. So that means that all we have to do in this problem is find the electric field at the origin due to just one of the rods, square it, multiply it by 2, and then take the square root. So then you'll end up with root 2 times your original electric field. So the electric field due to rod S, we're going to say is equal to 1 over 4 pi epsilon naught. dq is going to equal lambda dx. And then the R distance is from the origin to any little segment of the rod that you're going to integrate over. So our rod itself is starting at 0. So that means that the distance between the origin and any part of rod S is just going to be whatever position of that segment you care about given by X. So we would integrate that from negative 3L to negative L. You're going to get, let's see, negative lambda over 4 pi epsilon naught 1 over x, negative L to negative 3L. And that will give you, let's see, the negatives. I'm not going to bother trying to get rid of the negative signs yet. I'm going to write this out and then simplify it because otherwise I'm going to make a mistake. So you get something along the lines like this, which is equal to, let's see, get rid of the negatives, or swap them rather. So you get 2 lambda over 12 pi epsilon naught L then, which is lambda over 6 pi epsilon naught L. So that's the electric field due to just rod S, which means that the total electric field in magnitude must equal root 2 times that. So you're going to have root 2 lambda over 6 pi epsilon naught L then. So that is our electric field at the origin. Yes, perfect. All right, rod T is removed. I'm going to go ahead and delete my text now. Rod T is removed, and now the right end of the rod is at the origin. And rod S is then moved. Okay. Rod S is then moved with a speed in the negative x direction, and you want to draw the electric potential as a function of distance r between the origin. Okay. Um, let's see. So if the electric field goes like 1 over r, then because that's what we derived earlier, right? Was we derived a 1 over r expression, and that means that the electric potential should go like let's see, negative natural log. So, or actually just a positive natural log. We found, so you're going to have a positive natural log and no, it shouldn't be positive. It should be negative. Anyway, I'm just going to rederive an expression for the electric field, at the origin due to the rod real quick, just so I can double check this. So we got lambda dx over x squared. And we have bounds on, the bounds of the rod were whatever they were, right? That means that the electric field is going to be proportional to negative 1 over x, which means that the electric potential is going to be given by negative natural log. Sorry, positive natural log then. Electric potential will be proportional to negative integral of e dx, or e dr rather, which is going to equal natural log of x. Now, all that being said, we should expect that at when the end of the rod is at the origin, you should have an infinite potential. So let's see. Infinite potential, does that make sense? It should make sense because you can't get a positive charge there. Um, And then, yeah. And then it should approach 0 as rod S moves to the left then. So I would expect something along the lines like this. Uh, But the fact that they don't have a negative axis makes me think that the electric potential is not going to be negative. Um, okay. So let me go ahead and erase this real quick and let's see. So we know that this is a uniform velocity. So I'm going to say then that I don't want to do this as a function of time, though. This seems weird. I think I'm overthinking this, honestly. So the rod itself is 2L. So let me solve for the electric field when... No, that doesn't make any sense, though. Um, hmm. Let's see. Let me solve for the electric field actually when the rod is at negative 4L, negative 2L, just because I want to see exactly what's going on here. So we've got negative lambda over 4 pi epsilon naught 1 over x. So you're going to have a negative 1 over 2L plus 1 over 4L, which is lambda over 4 pi epsilon naught 1 over 4L then. Um, Yes, and then before we found that it was going to be a two-thirds, which means the electric field is getting smaller and smaller. You're going from an electric field of infinity to 2 over 3L to 1 over 4L. So it's going to keep getting smaller and smaller, which means that your potential must begin to kind of level off because your electric, not level off, but start to decrease at a constant rate. So I'm going to say something along the lines like this. This is a weird one. I'm trying to get some sort of visualization for this. And actually, now that I think about it, there's a much easier way of doing this, guys. Sorry, I'm kind of brainstorming. If you couldn't tell, this is my first time actually looking at these questions. So, it should look something like this. And then this is going to be end one of the rod. We'll call it XL. And then this is going to be XR, which is the right end of the rod. So, yeah, this is much easier actually. I don't really know what I was trying to do with the electric field equation, but this gives you potential as a function of distance, natural log of x from xr to xl then. Oh yeah, much easier. So you end up with something along the lines like this then. Natural log of xr over xl. Where XR and XL are where the left and the right and the left ends of the rod are respectively. Okay, so when both of them go to infinity, that means you're going to get a potential of zero. So when R goes to infinity, because that's where the right rod is, right, then you're going to have a zero potential. When XR is infinite, you're going to have an infinite potential, and then you're going to have when XR is at 2L and XL is at 4L, you're going to have natural log of a half. That doesn't make any sense. Um, should be ln of 2 probably. So, okay. So it should be a natural log equation then. Okay. So, yeah, I'm just going to draw it as a natural log graph. It's going to look something along the lines like this. Yeah. Okay. Yeah, that's probably about as best as I can do. I feel like I was vastly overthinking that one. Okay. Anyway, new non-conducting rod with negative charge density. Integrate, sorry, not integrate, indicate, if you couldn't tell, I'm kind of tired. It's the weekend, but indicate how a sketch of V0 at the origin due to both rods and S as a function of R would be different as both of them are moving. Okay, that's not too bad actually. So we would say that the value of electric potential, V0, would always be zero. The reason why is because they're both, let's see, they're both the uniform same charge density, just opposite signs. And they're both equal distance away. Yeah, okay. So the value of V0 would always be zero. This is because both rods have opposite charge, equal opposite charge, uh, always located same distance from the origin, uh, and since potential is a scalar, um, components are not necessary. Okay. Yeah, there we go. Literally it would just be the value is always zero. Actually, except for no, yeah, it's always zero. Okay. Um, yeah, all right, there we go. All right, I heard some stories about this one, LC circuits. You want to determine the inductor. You're given several charge capacitors and a voltmeter, and you want to determine how are you going to measures potential difference as a function of time. Okay, So the two quantities that I want to determine to get a linear graph is I would like to measure the period of oscillation of electric potential. We'll call that T, and the capacitance. Do we know the capacitors? Yes, we do. And the capacitance of our capacitor in the circuit, C. All right, describe a method. Repeat multiple trials. We'll say, not 6 or 7 times this time, 2 to 3 times uh, with the same capacitor, uh, and find the average of the period of oscillation uh, for each capacitor before swapping to a different capacitor. Okay. Indicate, part B is going to be not too bad because we know from our equation sheet that this is true. So then we know that T must equal 2 pi square root of LC because it's 2 pi over omega. So that means we can plot the period versus root C, and therefore the slope is going to equal 2 pi root L. So therefore, L will equal the slope over 2 pi squared. There we go. So that's our answer for part B then. Okay. Wow, this one's actually not too bad then. So, all right. In experiment 2, you're asked to determine the inductance. You have a battery. Oh, okay, not too bad then. You have a battery and you have a resistor. You measure I and dIdt. That is actually not too bad because we know that if you have different times, then I and dIdt, you can use those to. Yes, no, this is not bad at all then. You want to determine what L2 is. So how I would do this is that I is associated with the voltage across the resistor, right? V is equal to IR for the resistor. And then the voltage across the inductance should be given by negative L di dt then. So in terms of that, we could say that because 12 minus VL must equal IR, then we could actually use that to find the inductance quite nicely then. So we have 12 minus L dIdt equals IR. So that implies then that if we have, say, if we plot I. Actually, no, I'm going to simplify this or rearrange it. I is equal to 12 over R, which is a constant. It's 10 minus, let's see, L over R dIdt then. So what that actually means now is that means if we plot I versus dIdt, we will get a slope of negative L over R and a y-intercept of 12 over R then. So yeah, that works. So I am going to actually go ahead and create a data table. I still have Desmos open, so I'm going to go ahead and do that just so I can create my graph, and I can actually go ahead and show you guys the results of that then. So I'm going to go ahead and plug in my dIdt values. We got 280, 230, 150, 100, and 68. And then my I values are 0.4, 0.5, let's see, 0.75, zero point 0.9, and 1. There we go. All right. And let's see. All right. And let me go ahead and create, oh, that's not very nice, is it? Let's go ahead and create a linear regression. Okay. So got it. Okay, perfect. So I'm not going to actually create the graph on here because for number one, for the sake of time, two, I think you can all plot the data points correctly once you figure out exactly what should go on there. And three, I don't really think it's gonna help you guys too much. So okay. And of course I deleted my equation, but in any case, I remember what we need to plot. We're gonna plot I, which is in amps. It wasn't amps, right? I think it was actually milliamps. Nope, it's amps. There we go. So I in amps and di dt, which was in amps over seconds. So, so when we scale our axes, right, you're going to want to scale it, of course, so that you can fill as much of the grid space as possible. What I had for my equation was I said 12 minus L di dt equals I times R. R is 10. So in that sense, right, we could say, okay, well, that implies then that if I do I over di dt, I'm going to get 1.2 minus L over 10 di dt equals I. That means that the slope of my graph should equal negative L over 10 then. So L should equal negative slope multiplied by 10 then. Now I've actually got my graph plotted in Desmos and my slope in Desmos. Again, what you would want to do, of course, is plot your data in this grid space, approximate 2 points on the line and use those to calculate your slope and say which points you're actually using. But again, for the sake of time and because I don't think it's really all that useful for you to sit here and watch me plot the same data points that you're plotting, right? I'm not going to go ahead and do that, but my slope, according to Desmos at least, was negative zero. Yes, negative. So the two negatives will cancel 0.0003. So therefore, my inductance is 0.03 Henry, which is the units for inductance. Um, okay, there we go. All right. And for scenario four, you have, it looks like this is going to be a Faraday's law question. So you have a square conducting thing and time varying electric field, magnetic field. Indicate whether the induced current is clockwise, counterclockwise, or zero in the time indicated. So it's a cosine function, which means that the magnetic field is going to be getting smaller, which means that by the left-hand rule or by Lenz's law, you're going to have a counterclockwise induced current. So magnetic field uh, remains uh, out of the page, but is decreasing in strength. Therefore, change in flux is into the page. Lenz's law states the induced current must generate a field to oppose that change. Therefore, the induced current must be counterclockwise. Okay, there we go. Not too bad. I actually really like Lenz's law. All right, derive an expression for I as a function of all of that stuff. That's actually really easy. I'm going to scroll up. So I'm actually really comfortable with Lenz's law, guys. I don't know about you, but and Faraday's law for that matter. So, okay. So we can start off by calculating the induced voltage, which is going to be given by the magnitude of the change in magnetic flux with respect to time. Since the magnetic field does not vary with space, this is not too bad then, because that means that we're going to have ddt of B times A, because flux is equal to integral of B dot dA, which is equal to BA in this case. So there we go. So that's going to equal ddt of the area is going to be s squared. So ddt of s squared times the magnetic field, which is B0 cosine 2 pi t over t1. The derivative of a cosine is a negative sine, so we are going to have negative B0 s squared times 2 pi from chain rule, all divided by t1 sine of, it should all be absolute value anyway, sine of 2 pi t over t1. Since current is equal to voltage over resistance, then that is going to give us B0 s squared times 2 pi over R T1 sine 2 pi T over T1. There we go. All right. Um, okay. So yes, that is everything. And then part C is our final thing. So new square thing. Oh, I love these questions. Yeah. Not all of them actually, just part C. I love questions like this. New square loop has total side 2s and total resistance 2r. Indicate whether the maximum induced current and I don't know why I deleted my equation. I'm bringing it back. I need it for this actually. Not really, but you know. Okay. So you want to indicate whether the maximum induced current is greater, equal, or less than the original one. So you have two resistance and two and four times the area, which means that you're going to have a bigger induced current. By my equation, uh, the maximum current is twice as big due to the loop having four times the area and twice the resistance. I'm gonna go back up here. Sorry, my work's a little bit messy, but this is all the room I have on my screen. So by my equation, the maximum current is twice due to the loop having four times the area and twice the resistance. This is because s squared gets turned into 2s squared, and then r gets turned into 2r, which is going to equal a total of 2s squared over r. So the total uh, induced current doubles. All right, there we go. That is it for this free response question. Yeah, so thank you guys so much for watching. Hopefully you found this helpful, and hopefully you all got fives as well too. I found that I think these FRQs were actually easier than the mechanics ones. I didn't really see anything that tripped me up too much aside from that initial graph in question one. And even then, that's pretty nicely solvable or approximable, approximation wise. Pretty easy to approximate, especially if you have Desmos. So, have a great weekend, guys. Get some rest. You've definitely earned it after these AP exams. And try not to stress too much about your scores. They'll be out in July. Nothing you can do about them right now anyway. So enjoy the first half of your summer, and I'll see you guys in the next video. I'm going to try to get some more relativity videos and quantum mechanics videos up soon. Been a little bit bogged down with my actual job and everything, but hopefully more of those will be coming soon, so please keep an eye out. Anyway, have a good day, guys.